Okay, we shall get started then. Today we are continuing on in Chapter 7, and prior to the midterm, and I don't know if you guys remember any of this stuff, we talked about hypothesis testing, just kind of the introduction to hypothesis testing. And so Chapter 7 is all about hypothesis testing. And specifically, what we are doing is we will look at the t-test. Okay. Okay, and so in hypothesis testing, we established a few things, and we said a key piece of hypothesis testing, key pieces are we have hypotheses. Okay, and one is called the null hypothesis and the alternative hypothesis. Okay, and the null hypothesis is generally our quote-unquote status quo, nothing interesting. And basically, if this were true, then any results we see are just a result of random chance. Okay. Results in our data are due to random chance. Okay. And then the alternative is, something quote-unquote interesting is happening. Okay. So, and then we talked about, our evidence, which is the data. Okay. And then lastly, we talked about, well, I don't know about lastly, but we also talked about something called the p-value. And do you guys remember kind of what the p-value is? The p-value is a probability. It is the probability of observing our data. Okay. If what? Probability of observing our data, or I have to write something more extreme. If we assumed that the null hypothesis is true. Okay. And so before the midterm exam, let me figure out where to save this. I said, I think I used this example of, somebody, you're playing a game with your friend, and he's supposed to flip some coins, right? And basically, the more times it runs up heads, like the more he wins, okay? And so, if you played the game, if he flips the game 10 times and he won 70% of the games, you wouldn't really go out and accuse him of cheating, because the probability of observing 7 heads out of 10, if we assumed everything is fair and nothing weird is going on, the probability of that happening is quite decent, okay? There's a fairly large probability that somebody who flips the coin 10 times ends up getting 7 heads from pure chance alone, okay? On the other hand, if he played 100 games and he won 70% of those games, okay? In that case, you would start to suspect that maybe he's trying to cheat, because the probability of observing your data the probability of getting 70 heads out of 100, if we assume that the null hypothesis is true, if we assumed he's playing fairly, the probability of that happening is very rare, okay? And so in that case, getting 70 heads out of 100, or even 70 or more heads out of 100, is a rare circumstance. And because that probability is small, that causes us to doubt maybe our friend's honesty in this situation. Okay, and this is the concept that we're going after, and I hope this kind of jogs your memory a little bit. Okay, and so I'll just kind of write a quick recap up on the board of what I said. Okay, so we have a game, flip coins. Okay, and then if it lands heads, more often, your friend wins. Okay, so scenario 1, okay, 10 flips, friend says 7 heads. Okay, this is quite possible. This result is quite possible from random chance alone. Okay, so we do not doubt our friend's honesty. Okay. On the other hand, scenario 2, 100 flips. Okay, and the friend says 70 heads. Okay, this is quite the probability of this happening, of this result happening from random chance alone, into fair coin, is very, very low. Okay, so we start to question our friend's honesty if this were to happen. Okay, now it is possible. It's in either situation. Neither situation proves that he is for sure playing fairly. Like scenario 1, we don't doubt our friend's honesty, but he could also be lying to us. Okay, it's just that 7 out of 10 is not enough to kind of trigger some flags, right? On the other hand, getting 70 heads out of 100 causes us to doubt our friend's honesty, but at the same time, it is possible, technically it's possible that he just happened to get that lucky, okay? It's like a 1 in 100,000 or like 4 in 100,000 chance of this happening, but it is technically not impossible, and so in that case, our friend could have been, quote, so unlucky that now we're questioning his honesty, okay? But this is kind of the way hypothesis testing works, okay? We assume that the null hypothesis is true, and then we say, if the null hypothesis is true, what's the probability of getting our data. That number, that probability, is called the p-value. It's the probability of observing our data if we assume the null hypothesis is true. Okay? And so the conclusions that we make are, if the resulting p-value is large, okay, we say we have no evidence to reject the null hypothesis. Okay, and on the other hand, if the resulting p-value is small, okay, we say we have evidence to reject the null hypothesis. Okay, notice when we say not rejecting the null hypothesis is not the same thing as accepting the null hypothesis. It also does not mean that the null hypothesis is true. Okay, so, you know, to kind of help you along here, if you think of a criminal trial, okay, the juries always come to the conclusion of either guilty or not guilty. Okay, the jury never says we find the defendant innocent. They would never say that. Okay, they say either the defendant is guilty or not guilty. A not guilty verdict does not mean that the defendant is innocent. The defendant could be innocent. The defendant could also be guilty, but did a very good job of getting rid of all possible evidence. Okay? So a not guilty verdict just means there was not enough evidence presented by the prosecution to convince the jury that that the defendant is guilty. Okay? So not rejecting the null, basically a not guilty verdict, is not the same thing as saying the defendant is innocent. So not rejecting the null is not the same as accepting the null. Okay. Okay. On the other hand, if you've rejected the null, that is basically saying you are accepting the alternative. Okay. So rejecting the null is equivalent to accepting the alternative. Okay. All right, so we will introduce the t-test here, okay? Okay, the t-test is a hypothesis test that we use to compare the means of two populations by observing the means of samples taken from those populations. Okay, so this kind of fits in with the big theme of statistics, which is making conclusions from limited data. The big idea is, we can't observe the populations directly. So if we observe just samples, can we look at the samples and make conclusions about the populations? And the answer is yes, and the t-test is one way we can do that. So here, you could have population 1. For example, we could say population 1 will be women, and population 2 will be men, okay? And perhaps we are looking at the mean, I don't know. Let's see. Well, I don't know. The mean whatever, okay? All right, we'll go there. Okay, so we'll say the mean salary, okay? So we'll look at mean salary for women, and we'll look at mean salary for men, okay? And so the question is the mean salary for women the same or different than the mean salary for men? All right. I heard there is a very interesting discussion on this on the Freakonomics radio podcast. I don't know if you guys ever listen to radio podcasts, but it was very. I feel like I learned a lot from it, and so, I think we hear a lot of things like women make 78 cents on the dollar or something compared to men, and that would be if you looked at the entire female workforce versus the entire male workforce, and even in like related segments of the economy, there's still a discrepancy in pay, but the discrepancy is not present for recent graduates. So people who just enter the workforce, there's that discrepancy does not exist. It's but basically I think the argument made in this podcast, and they're talking to this economist at Harvard University. She has done many studies on this phenomena, and her premise is that men and women make different career choices or choices in their career development, where basically because women often choose, well, men don't have the choice of becoming pregnant, and so because of this differentiation, this ends up causing the difference in pay. But there's a very interesting thing, and I recommend looking up Freakonomics podcast and listening to the story. But anyway, this is not it. We're not going to be able to discuss this, but let's say you were just curious about, population will be women and men, and maybe this is too big of a population. We could say like women in, I don't know, education professions and men in education professions or something like that. You define some kind of population, you define the quantity that we're looking for, the mean salary and the mean salary here, okay? And then, of course, we can't observe this directly, okay? So what we have to do is from the population, we observe a sample. Okay, so, sample 1 will be women, and sample 2 will be, men. And so you will have two sample sizes. N1 will be, I don't know, let's say we looked at 22 women and we looked at 25 men, okay? The sample sizes don't have to be the same. And from the sample size, from the samples, you get a sample mean, okay? Size, mean, and standard deviation, okay? So I'm going to just completely make up numbers here. So we'll say women in education sector and men in education. I have no idea. These are ill-defined. Okay. But let's say you've figured out this problem. You're able to obtain a random sample of women and a random sample of men. Okay. So I don't know. I'm going to make up a number here, 62,000, and we will say 64,500, and the standard deviation will be 3,500, and the standard it probably needs to be bigger than this, but standard deviation here will be 4,200. Okay, just maybe this is primary education. I have no idea. All right, just making up numbers. Okay, so don't hold me to this. Okay. Oh, and I'm sorry. This is S1 because it's the standard deviation of population of sample 1, and this is S2, the standard deviation of sample 2. Okay. So these will be our values. And so what we see is that in our samples, we have different sample means. Well, if our samples have different sample means, does that mean the populations have different sample means? Okay, so we'll answer this. Every time I write a new exam, it's always a mystery how long it needs to be. So, okay, so we'll work on this. Okay, so these are our values. Okay, so we'll work through this, and we're going to establish our hypotheses. Okay, so the hypotheses, our null hypothesis, I'm going to write this in words first, will be that men and women have the same mean salary in the population. Okay. Now I know I said the null hypothesis is, quote, this status quo statement, and if we know things about this does not seem status quo, but this is the, quote, not interesting thing happening, meaning that these two populations have the same mean. That may be of interest in of itself, but this is kind of the default setting, and so symbolically, to write that men and women have the same mean salary in the population, we would write the mean, so mu for men is equal to the mu for women. Okay, so this is one way to write it. Or another way, and this is exactly equivalent, would be to say that the difference, if I were to take the mean female salary, subtract off the mean male salary, that difference would be 0. Okay, so these two things are saying the same thing. All right, so that would be our hypothesis, null hypothesis. This one's the null. And then the alternative Yes, question.
Does it matter
If I wrote the M over here and the W over there, I guess. This probably should be a W, and this should probably be an M, because I wrote women for sample 1 and men for sample 2. But
so for the equation one, it does matter.
You know, for the null hypothesis, it does not really matter. What matters is, in the alternative hypothesis, the direction of the sign that we're going to use, okay? So the alternative, okay? We have a few choices for the alternative hypothesis. One is we can take on what we call a non-directional alternative, okay? So I'm going to just start off with the non-directional alternative. And this is going to be something like women and men, or men and women, however you want to write it, have different mean salaries. In the population. Okay? So that's the non-directional. And then we have two possible directional alternatives. Okay? So I'll say directional 1 and directional 2. And you don't have to worry about which one's one. But, okay, so directional alternative 1 will be women have a larger mean salary than men in the population. And men in the population. Okay, and then directional alternative 2 will be men have a larger mean salary than women do. Women do in population. Okay? Or, you know, if you wanted, if you care, you know, directional 2, I wrote men have a larger mean salary than women do in the population. I could have written the exact same thing, just using different words, and I could have said women have a smaller mean salary than men do in the population, okay? So, you know, men having a larger is saying the same thing as women having a smaller mean salary. So your choice of words is up to you, okay? So directional alternative 1 symbolically would be mu for women is greater than the mu for men, okay? Over here, directional alternative for this would be mu for women would be less than mu for men. It's too bad that M's and W's are in this mu, the way I write the mu, they all look the same. It looks like I'm just writing squiggles, little mountaintop ranges. But maybe I should write F for female. But are we okay with this? All right, so this is how we can express our alternatives.
And
yes?
the non-directional, it's the non-equal sign?
Yeah, oh, I'm sorry. That's a very good point. I left that off. Okay, so the non-directional alternative would be mu for women is not equal to the mu for men. Okay? And again, equivalently, you can also write it as mu w minus mu m is not equal to 0, or mu w minus mu m is greater than 0, or mu w minus mu m is less than 0. Okay, so those are all effectively the same thing. Yes?
Do mu w is greater than 0 if it's...
So you would not do mu w by itself. It would be mu w is greater than mu m, or mu w minus mu m that difference is greater than 0. Yes?
Why would it be less than or equal to or greater than or equal to?
So you don't put the less than or equal to or greater than or equal to in the alternative because the null hypothesis has the equal to.
Oh, okay.
Okay? So the null hypothesis has the equal to, so the alternative is either going to strictly be greater than, less than, or not equal to. Okay? All right, and so, you know, we are supposed to pick our hypotheses before we look at the data. I didn't do this quite right, but so we can say, you know, so let's say we choose the alternative, and so we have 3 choices here, okay? And we'll take a look. If we, really the only 2 ones that are compatible with our data are the non-directional alternative or direction 2, okay? Because right now, if we had picked directional alternative 1, our data just does not support this alternative, right? Our data currently shows that even in our small sample, we are seeing a mean salary that is less for women than it is for men, okay? And so this directional alternative is not supported by our data, okay? And so this is called the check for directionality. I call it kind of just like a common sense check. All right, so anyway, part of the problem is, or you know, hypothesis testing is to write your hypotheses. Okay, so let's say our hypotheses are null hypothesis will be symbolically the mean for women is equal to the mean for men, and then our alternative will be the mean salary for women is greater than the mean salary for men. Okay? If we looking at the data we collected, okay, we see that y bar for the women is equal to 62,000 and y bar for the men is 64,500. Okay, so our data does not support the alternative hypothesis. Okay, so at this point, if this is our alternative hypothesis, we have no evidence to support the alternative. We would have no evidence to reject the null hypothesis. Okay, so you know we can stop here. Reject the null hypothesis. Okay, so this is called our directionality check, where you just kind of make sure that the data you are using could even possibly support the alternative hypothesis. Okay, because if it doesn't, there's no sense in continuing on with the math. I mean, you could, but it's just not going to happen there. Okay. Okay. So, all right. So we'll continue, and we'll say we've used one of the other alternatives here. Okay. All right. So we observe a sample. All right. So now we will do So we will say our hypotheses, our null hypothesis will be okay, so this is what we call a directional alternative. And let's see. Okay, and so we're going to conduct a t-test, okay? And so the way the t-test works is we're going to find basically a test statistic, okay? So our test statistic is almost always going to be in the form of our observed value minus kind of the expected value if null is true divided by the standard error. Okay, and this will apply to I don't know, a bunch of situations, okay? So, you know, we look at the difference between what we observed and what we would expect, and we're going to look at that difference and compare it to the standard error. So it's very much like a z-score, okay? So a z-score for the normal distribution is, you know, if we say the average is 100 and someone is out at 120 and the standard deviation is 15 or something like that, okay? Basically, what the what the normal distribution says is that we're expecting things to be close to the mean, okay? 120 is higher than the mean, so that difference is 20. Is that a big difference? Well, we compare it to the standard deviation, okay? We're doing something similar here. We're taking an observed value. We're going to compare it to the expected value if the null hypothesis were true, and we're going to compare that difference to the standard error. Okay. All right. So our observed value. Okay. So in our case, we're going to say the observed value is the difference between the female's average salary and the women's average salary and the men's average salary. So it'll be y bar for the women minus the y bar for the men. So in our case, it'll be 62,000 minus 64,500. Okay, so we are getting a difference of negative 2,500. Okay. If the null hypothesis were true, what would we expect the difference between y bar for the women and y bar for the men to be?
0, 0.
We would expect that difference to be 0, right? So y bar women minus y bar men expected to be 0. Okay, so our test statistic will be negative 2,500 minus 0. So effectively just negative 2,500 on the top divided by our standard error. Okay. And so because for t-tests the expected value is almost always 0, we often will just say for a t-test this ends up being y bar 1 minus y bar 2 divided by the standard error. Okay, it's technically y bar 1 minus y bar 2 minus 0. Okay, but because subtracting off 0 does nothing, sometimes it's just left off. Okay. The standard error, I think this quantity will be familiar, is the same standard error that comes from our sampling distribution for a difference between two means, which is going to be S1 squared over N1 plus S2 squared over N2. So our standard error is going to be the square root of 3,500 squared over 22 plus 4,200 squared over 25. And if I punch this in, that's a big number. Okay, I get a standard error of 1123. So $1,123.57. So my test statistic ends up being negative 2,500 divided by 1123.57. Just want to pause for a minute here and just make sure everybody's okay with everything I've done so far. Okay, so we've set up our hypotheses. We're calculating out our test statistic. Okay, so on the calculator, I'm going to type in negative 2,500 divided by this value and my answer. So I get negative 2.22.
Should you round it to 23?
Huh?
Should you round it to
Oh, you're right. I should round it to 2.3. Okay. Well, I could leave it 2.25. I'm going to just leave it negative 2.225. Okay. All right. So what we're going to do now is we're going to look up this value in the t table. Okay. So. So now we will look up, we will look this up, this test statistic in the t table. All right. So let's go. All right. Actually, let me go on to the next page here. So we'll have this. So I'm just copying stuff I had from before. Our null hypothesis. And then our test statistic. All right, so how do we use our t-table? Okay. Well, we need to have our degrees of freedom, okay? And again, figuring out the degrees of freedom, we're going to just approximate it by saying the approximate degrees of freedom is n1 plus n2 minus 2. So in our case, we have 45 degrees of freedom, if I added this up correctly, okay? And so to use the t-table, we go to the t-table, we look for 45 degrees of freedom, okay? We don't see 45 degrees of freedom, so we are going to look at, if you can't find the exact number of degrees of freedom, you always round down, so I'm going to go to 40 degrees of freedom, okay? So this is the row for 40 degrees of freedom in the t-table. Okay. So we can't can't find df equal to 45, so round down and use 40 degrees of freedom. Okay, I'm just going to copy this relevant piece of the okay. Okay, so what we have is that, this is 40 degrees of freedom, and what we're going to do is we're going to see where 2.225 fits in our table here, okay? And because the table is symmetric, even though I have a negative 2.225, I'm going to just ignore the negative sign and look for 2.225. Okay, so look for where 2.225 fits on the table. Okay, and so for 40 degrees of freedom, 2.225 fits in between 2.123 and 2.423. Okay? And so this means the corresponding upper tail probability, or because it's now negative, it'll be the lower tail probability. So just the corresponding tail probability is in between 0.01 and 0.02. Okay, so basically you go, you go to that row, 40 degrees of freedom, see where 2.225 fits, and then you look at the top of the column and you say, okay, the corresponding tail probability is going to be between these column headings. All right. So if I had to illustrate this, the t-distribution looks very much like the normal distribution. Okay. And what we're saying is that 0 goes in the middle. If I drew a line at negative 2.123, then the area over here in the area over here would be 0.02. This area is 0.02. Okay. However, if I move that line over to the left even further, at negative 2.423, then the area over here would be 0.01. Okay, 0.02. This is the entire area to the left. This chunk is 0.02, and then this area over here to the left of negative 2.423 is only 0.01. Okay, which means what I'm doing is I'm not drawing it there, I'm drawing a line in between at 2.225. And so the amount that I have shaded to the left of negative 2.225 has to be more than 0.01 but less than 0.02. Okay, so my tail area is between 0.01 and 0.02. Okay? And that's all we can say at this point. All right? We can't get anything more accurate than that unless we go to a computer. Okay? But if you're using a table, all you can say is, well, it's going to be somewhere between 1 and 2%. Okay? You can only give almost always you're going to be giving a range of values. You're going to say, well, it's between this and this. Okay? Only if in the rare circumstance where you get exactly one of these values, so if you happen to get 2.704 as your test statistic, then you can say, okay, my tail probability is exactly 0.005. Okay? But almost that happens very, very rarely. So almost every other time you're going to say, okay, my tail probability is between these two values here. Is that okay? All right, so this is my tail probability, and so what this says, okay, so my tail probability is between 0.01 and 0.02. Okay, so let's write that down. So my tail probability is between 0.01 and 0.02, or I can, you know, in shorthand write this 0.01 is less than my tail, less than 0.02. Okay. What this says is that if the null hypothesis were true, okay, so in our case, what was our null hypothesis? That male and females have the same average salary in the education field, or something like that, okay? So if that statement were true, okay, so if, you know, men and women have the same average salary in education, okay, in the education sector, then the probability that two random samples would have a you know, mean difference of, what was it, 2400 or 2500, 24? I forget. What? 2,500, okay. A mean difference of $2,500 or more, okay. So the probability that two random samples would have a mean difference of $2,500 or more is between 1 and 2%. Okay, 0.01 and 0.02. So it is possible that we draw, you know, that men and women have the same average salary, and just from random chance, it's technically possible that I just got this weird sample where the difference I observed was $2,500. Okay? Could that happen by random chance? Sure, it could happen by random chance. How often does it happen? It happens between 1 to 2% of the time. Okay? So the question now is, well, are we going to say 1 to 2%, that's a non-negligible amount, so I'm not ready to say this provides evidence that there's a difference between male and female salaries. Or do I say, well, 1 to 2%, that seems pretty unlikely, so I'm ready to conclude that this provides some evidence that men and women have different average salaries. The second one, okay. And well, so people could disagree here. And this kind of, what you decide reflects kind of your aversion to making how cautious you want to be about the decision. Okay, so I'll say, you know, at this point we have two possible choices. We have two possible conclusions. Okay? One possible conclusion is, okay, you know, it is possible that my sample data was a result of random chance. Well, it's always possible, okay? Okay, I am not ready to dismiss, so I'm being very verbose in writing all of this out, okay? In the future, I'm just going to say, I'm not going to reject the null hypothesis, or I'm going to reject the null hypothesis. But here I'm going to be very verbose. So, you know, when we make future conclusions, you can kind of look back to this. So I am not ready, you know, to dismiss the possibility that it was random chance. Okay, so you know, in our case, it's 1 to 2%, right? I'm not ready to dismiss the possibility that it was random chance, so I will not reject the null hypothesis. Okay. The other conclusion is it is possible. So these both start off with the same statement here. Okay, it is possible that my sample data was a result of random chance. Okay, but the probability that my data happens, or the probability that my data happened from random chance is very small. Okay, so I am ready to dismiss the notion that it resulted from random chance alone. I will reject the null hypothesis. Okay, and this line of thinking applies to pretty much all hypothesis tests. Okay, so I tried to make these as generic as possible. Yes, question?
So what exactly is very small? Is
Yeah.
it less than 1%?
Okay, yeah, so here we're, you know, if we reject the null hypothesis here, we're saying, you know, smaller than 2% is very small, okay? And I think, you know, smaller than 2%, I think most of us would reject the null hypothesis, right? Because if you think about it, if we were to do a card trick here, and I said, you know, pick a card, any card, and you pick a card, and then I say, and I correctly guess the card that you drew, I think you would say, wow, right? Technically, I have a 2% chance of being right. But I don't think anybody says, oh, you just happen to get that lucky 2% guess. Okay, I think your initial response is to say, oh, wow, how'd you do that? Okay. So I think there's something to it. Okay, so where do we draw the line? Okay, this is a very good question. Okay. Can I flip to the next slide here? Okay. So, well, actually, did we finish the previous problem? So what we said is we have two choices. So, you know, probably, you know, what we said was our tail area was between 0.02 and 0.01, okay? So in our case, our p-value, our tail area is the p-value, equals the p-value, okay, when we have a directional alternative. Okay, so our p-value is between 1% and 2%. This feels small to us. Okay, so we will reject the null hypothesis. okay? And we conclude that our data provides evidence that the mean salary for women is lower than the mean salary for men. Okay, so yeah, when I said, so we will reject the null hypothesis that encompasses that entire paragraph that I had written earlier. You know, our p-value is small, you know, it could have resulted by random chance, but it's so small I'm ready to ignore it. So we're going to conclude that the okay. So what is a large and what is a small p-value? Okay. Well, this depends on our choice of alpha, okay? So prior to doing all of the math, we are supposed to pick what we call a significance level. All of our computations we should pick a significance level. Okay, and the significance level is called alpha. Okay. Over time, alpha equals to 5% has become our kind of the gold standard, okay? So generally, alpha equal to 0.05 has become the quote standard. It's probably something around 5%, but there's nothing magical about 5% in of itself, okay? A lot of times if you want your paper to be published, if you've done some research, you're hoping that your p-value ends up less than 5%, okay? But there's, and there's a lot of people argue about this, and this has come under a lot of criticism, okay? But you know, 5% has become the standard, but really, we can choose any alpha that we please. We can choose any level alpha we want. 5% is probably the most common, but you know, alpha equal to 10% is acceptable. Usually, you don't really go larger than alpha 10%, okay? And you know, sometimes we use alpha equal to 1%, or you know, or something in between, okay? But this 5% value, 0.05, it is an arbitrary value, but it's kind of just become established. For example, it should be somewhere around 5%. There have been done, lots of studies have been done, and the value should be something around 5%. But the value 0.05 in of itself is a bit arbitrary, okay? Kind of like in the United States, the age of majority is 18, okay? when you turn 18, on your 18th birthday, you can vote, you can enlist in the military, you can do all sorts of things, okay? You are now deemed an adult, a responsible adult, and you are responsible for your actions. Is there really anything different between a 17-year-old who is 17 and 364 days old and an 18-year-old? No, not really, okay? But in the eyes of the law, there is a distinct difference, okay? And, you know, the age of majority should be something around there, right? That's, I think studies have been done, and that's kind of where your, whatever, prefrontal cortex has developed most of its capability. So it should be something around there, but there's nothing magical about the age of 18, but yet over time we have simply accepted this, and so, you know, this is law now, right? And so the same thing with this value of 0.05. It should be something around there. There's nothing magical about it. But, you know, for better or worse, this has become the standard value that we use, okay? And so our decision criteria is if our p-value is less than alpha, we reject the null hypothesis. And if our p-value is greater than alpha, we do not reject the null hypothesis, okay? So in general, you know, alpha is 0.05, and so if your p-value ends up less than 5%, you reject the null. If your p-value ends up being greater than 5%, we say, well, you don't have enough evidence to reject the null. Does this feel okay? Yeah.
What if it's equal?
If it's equal, now that happens very rarely. That means you happen to get that one value that's exactly in that column. And then you have to make a choice. Okay? You have to say, well, do I want, you know, and this is the problem, right? If I don't, okay, so, you know, should someone be prosecuted if they sold cigarettes to someone who's 17 years old and 364 days old? Or, you know, I don't know, 1 minute before their birthday, okay? If the transaction took place 1 minute before the birthday, should they get in trouble? You know, and if we're very strict followers of the law, then yes. I don't know, you know. These are, it's hard, and this is the problem where you draw such a harsh line at an arbitrary value of alpha, okay? This is, so, you know, what do we do when it's equal? Then you have to make a choice, but whatever. That rarely happens, okay? It's rarely the issue. Let's take a 10-minute break here, and we'll come back and we'll talk more about hypothesis testing.